In this video, we shall look at a couple of problems associated with atomic physics. Problem 1. An electron makes a transition from n equals to 4 Bohr orbit to the n equals to 2 orbit. Determine the energy and momentum of the photon created in the process, and assuming that the hydrogen atom was initially at rest, determine the recoil speed of the hydrogen atom when this photon is emitted. So let's do part A. Energy associated with nth orbit equals minus 13.6 over n squared, and the unit is of course electron volts. If the unit joule is required, then we have to multiply this result by the electronic charge. And in that case you will get the following expression: minus 2.18 times 10 to the power minus 18 over n squared joules. So energy of the photon created for such a transition is given by the following expression. It is energy associated with the initial orbit minus the energy associated with the final orbit, which is minus 2.18 times 10 to the power minus 18 over the initial quantum number is 4, so 4 squared, minus 2.18 times 10 to the power minus 18, and the final n value is n equals to 2, so 2 squared. This result can be compactly rewritten in the following manner: 2.18 times 10 to the power minus 18 times 1 over 2 squared, so that is 4, minus 1 over 4 squared, so that is 16, which will give you 4.088 times 10 to the power minus 19 joules. So this is the energy of the photon created in the process. Now let's look at the momentum of that photon created in this process. The momentum of that photon and the energy of the photon, namely this, are related in the following manner. The energy of the photon equals the momentum of the photon times speed of light. So therefore the momentum of the photon is the energy of the photon divided by speed of light. Now we use this expression for the energy of photon because photon is massless. So the usual expression momentum equals mass times speed would not work here. Substituting the value of energy that we have found above, 4.088 times 10 to the power minus 19 joules, speed of light is 3 times 10 to the power 8. The momentum of that photon can be determined in the SI unit, and its value is 1.363 times 10 to the power minus 27. The unit is kg meter per second. So we shall jot down the answers to part A here. Part B. Assuming the hydrogen atom was initially at rest, determine the recoil speed of that hydrogen atom when this photon is emitted. So let's do a schematic sketch. So this is the hydrogen atom, and you have photon emitted like that. Photon with some momentum as calculated here, P. Because the momentum is conserved, the hydrogen atom would move in opposite direction with some speed v. So this is called the recoil speed of that atom. What is this speed? Using the conservation of momentum, we know that the momentum of the hydrogen atom must be the same as the momentum of that photon here. Momentum of the hydrogen atom equals to the mass of the hydrogen atom. In a hydrogen atom, there is one electron and one proton. So all we have to do is to sum up these two masses. The mass of the electron is about 9.11 times 10 to the power minus 31 kilograms. The mass of the proton is 1.67 times 10 to the power minus 27 kg. And the speed is v. This is the recoil speed of that atom that we want to calculate. So this entire expression refers to the momentum of the hydrogen atom after the hydrogen atom emits photon like that. And this entire expression equals to P, where P is that number, 1.363 times 10 to the power minus 27 kg meter per second. And from this expression, V can be solved. Solving for V, we get the following number, 0.816 meter per second. And that solves the problem. Problem 2. Singly ionized helium, a hydrogen-like system, has one electron in the orbit corresponding to n equals to 1 when the atom is in its ground state. Find the energy of the system at the ground state and also the radius of that ground state orbit. When we say a hydrogen-like system, we're referring to the following system. We have nucleus in the middle and one electron orbiting that nucleus at some orbit. If the number of proton in that nucleus is 1, then we are dealing with a hydrogen atom. If the number of proton in the nucleus is 2, that means we are dealing with a singly ionized helium. Ordinarily, a helium atom consists of 2 protons and 2 electrons. When one of the electrons is knocked out by some process, leaving with such an hydrogen-like system, the resulting system is known as a singly ionized helium. Number of protons in a given nucleus is represented by the atomic number Z. For example, hydrogen's atomic number is 1, the atomic number for helium is 2, and so on. So the energy of such a system when the electron is in the nth orbit is given by the following expression, minus 13.6 z squared over n squared. And in this case, the value of z is 2, and since it is the ground state, n equals to 1. So the energy is quite simply minus 13.6 over 1 squared times 2 squared in the units of electron volts, which will give you minus 54.4 electron volts as the answer for part A. The radius of the nth orbit, let's call it r sub n, so this is part B, is given by the following expression. It is n squared over z times a constant a naught. The a naught, the Bohr radius as it's known, has a value of 0.0529 nanometer. And by definition, the Bohr radius is the radius of the smallest orbit of the hydrogen atom. So for a hydrogen-like system, this expression can be used to calculate the radius of the orbits. So for this system that we have in this problem, the radius of the ground state orbit, R1, is therefore 1 squared times a naught, which is 0.0529 nanometer, over z, the atomic number of helium, which is 2. And that's going to give you the following answer, namely 0.0265 nanometer. And that solves the problem. As always, thank you for watching.